So, online students, welcome. We are in 9.2, talking about estimating a mean. So to use that formula, you have to have a certain amount, you have to have certain stuff known about your data. You have to have a normally distributed x-bar, and that's either x is normally distributed or the sample size is at least 30, right? And, okay, both these things have to occur. You also have to know the value of sigma, the population standard deviation. Okay, the population standard deviation. So remember last time we did an example. So let's do a problem. Here's a problem on page 432. I'll read it for you. Okay, it's number 17. It's a Gallup poll of 547 adult Americans employed full or part-time, and this was conducted on August 13 through 16 in 2007. Asked, how much total time in minutes do you spend commuting to and from work in a typical day? So survey results indicated that x-bar was 45.6. And it's hang on. I think Jennifer's right.
Yeah, because 9.2 is if you don't, if the
right,
if it's unknown.
Right. Okay. Oh, sorry, you guys. Okay. Let me find a. Okay. Okay. So it's sticking with the criteria from. Actually, it's 9.1. You guys are right. Thank you. That's 9.1. Okay, so sticking with the criteria from 9.1, standard deviation known, x-bar normally distributed. Okay, let's try this problem. We'll get back to the travel to work problem in a very short time here. Okay. It says this is page 418, number 33. I guess I can write that. It says, every Monday, the Energy Information Administration determines the national average gasoline price by collecting retail prices for gasoline from a sample of 900 retail gasoline outlets from across the nation. Did you hear about this, right? Today, nationally, average price of a gallon of gas is blah, 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 right? On July 14th, 2008, the EIA reported a national average retail price to be $4.113 per gallon. Okay, so that came from their sample. Okay, that came from their sample. Assuming that the population standard deviation is 11 cents per gallon, construct and interpret a 95% confidence interval for the national mean price per gasoline. Okay, so we want a 95% confidence interval for mu, the nationwide true mean price of gasoline. Okay, so the key here is construct a 95% confidence interval for the mean. Okay? So because we know the value of sigma, and we certainly have a big enough sample size, yeah? Okay, so our formula is there, okay? So x bar, we have it. Sigma, we have it. N, we have it. And now we need the z-score that's based on 95% confidence. So again, the way we get that, normal curve, we want the cutoff values that contain the middle 95% of X bars for samples of size 900. Okay? So, yeah, so you want to take 1, the entire area, subtract the 0.95, so you have 5% left over, chop that in half, and you have 0.025 or 2.5% in each tail. Okay? And for you guys online, you do the same procedure for any level of confidence. Confidence in the middle, 1 minus, chop the leftovers in half, and then your z-scores in the formula are these guys. Okay? So then grab your handy dandy z-table, and if you look for 0.025 probability on the left, and remember for probability you're looking at the middle of the table, so you find 0.025, and actually this one comes out even. Your z-score is negative 1.96. Agreed? Everyone? Yeah? So that z-score is negative 1.96. And so the z on the other side?
Positive.
Positive 1.96, yeah. Due to symmetry. Okay. Okay, so now we have all of our pieces for our confidence interval. Let's plug and chug. So we've got 4.113 minus 1.96 times sigma, which is 0.11 over root 900, 2, and then all the same stuff on the other side with a plus. Okay. And so what do we get there, gang? Let's round to, I don't know, 2 or 3 decimal places. Yeah, Mike?
I think I got the lower.
Lower bound, what'd you
Yeah.
get?
What decimal place are we rounding it to?
2 or 3 is good.
Okay, 4.106.
4.106, thank you. Go ahead, Jordan, what do you have?
4.120.
4.120, thank you. Everyone agree? Okay. So we are 95% confident that the mean price of all gasoline in the United States on the week of July 14th, 2008 was between $4.106 and $4.120 per gallon. Okay, let's write that. And again, I'm always going to ask you to interpret. Interpret. So tell me what this result is telling you. And you always need to relate it back to the problem. Okay? So we are 95% confident. And you can start all confidence intervals that way. I am X% confident that the mean price of gas per gallon on July 14th, 2008 was between $4.106 and 4.120 per gallon. Well, I guess we already said per gallon. So we can leave that. An administrator of a rural town finds that the mean price of gasoline for all 5 gasoline stations in her town is $4.26 per gallon. Should she conclude that the interval is inaccurate? So let's say in her town, the mean price for gas is $4.26. What do you think about that? Yeah, Mike?
Maybe she lives in a city where they charge more for gas.
It says in a rural
Oh,
town.
no, no.
Oh, yeah, it's hard to beat that.
I don't know, what do you think? Maybe, is it just costing more here because it's the transportation of getting gas out there? Is it, I don't know. You'd think it would be cheaper in a rural town. It's usually more in a city. Maybe she should question if the gas stations in her town are overcharging. Scott?
Maybe there's not as many gas stations in the town, so they have a monopoly.
Yeah, maybe, yeah. It says there's
There's
only
five of
5
them.
in the whole town, so,
Yeah.
yeah. Courtney?
Maybe it's like driving down 5, how you don't have a lot of, like cities in between.
Choices?
So it's right there, of course you're gonna charge more, or like the gas station on right off of.
Because when you have to have it, you have to have it,
It's
right?
gonna charge a lot more than a gas station that's like in the middle of, that's not getting hit or isn't as necessary.
Yeah.
One that's in like the middle of a highway that doesn't have a lot of
Right.
cities on it.
Right, yeah, so maybe they're secluded enough to where they kind of got a monopoly on gas for quite a distance around. Yeah, who knows? So there's definitely some questions to be asked though, yeah? Especially if they're overcharging.
So how-
Okay,
So how do you answer that?
Yeah, exactly. How would you answer this?
well, if I put this on a test, any of those things we just talked about would be fine. Just use your brain. It's not, there isn't a right answer. It's just something to discuss, something to think about. Maybe this is happening, or maybe that is happening. Just, just use your head. Yeah. Okay, so last time we concluded, you can also do this problem on your calculator. We need to take a look at that because, it's so nice. So, you've got your TI calculator. And the directions for this is on my website, on the tests menu handout. You want to hit Stat and 2 right-hand arrows over to the tests menu. Let me get the glare off of that puppy. I always struggle with this, don't I? I gotta play with this thing more. So Stat, 2 right-hand arrows over to the test menu. So this is gonna be the menu we're gonna use from here on out, pretty much. And you want to go all the way down to number 7, which is Z interval. So once you get into Z interval, so Z interval is exactly this formula, exactly. Okay? Once you get in here, if you have the data to enter, you want to choose stats. If you have raw data, you want to choose data, and then it'll ask you for the list where your data is kept, and you'll enter that. So sigma, 0.11. X bar, looks like we've got 4.113. N was 900. And then you're going to enter your confidence. So C level is confidence level. And calculate. And there you have it. 4.106 to 4.120.
Is B online that didn't have all the listings? I didn't have.
Go over to stats, Erica. Go up here and over to stats, hit enter. There you go. Okay. So then the margin of error is half of the length of the confidence interval. So you can take the upper bound, subtract the lower bound, divide by 2. And you'll get that, it's a distance, okay? It's a distance. So again, last time we talked about the precision of the confidence interval. If the confidence interval is too wide, your precision is poor. The narrower it is, the closer you've kind of zoomed in on mu, and your precision is better. But again, that comes with a price, because remember last time we saw confidence level goes up, interval gets bigger. Sample size goes down, interval gets bigger, less precise. So let's say you want to get started on a study and you want to know sample size will meet a certain goal. So let's say that you have your, you have a set level of confidence. And margin of error. So you know how wide, you know how close you want to zoom in on your parameter of interest. Here it's a mean, okay? So you would start out in your study with a goal, okay? So remember, we took the margin of error, which is this part of the confidence interval. So that's the E. And we solved it for n. So you're setting your margin of error in advance. You're setting your confidence level in advance. Population standard deviation is set because it comes from the population. And you can figure out what sample size will get you there. So if you solve this thing for n, you get n equals z of alpha over 2 times sigma divided by e all squared. And then you're always going to round up to the nearest next biggest number, no matter how small your decimal is. Okay? So, and you don't have to derive this, but that's where it comes from. Just use the formula. So for example, let's do this one. I'm on page 420. Page 420, and this is number 45. Okay? So it says, a Gallup poll conducted May 20th through 22nd, 2005, asked Americans how many books, either hardback or paperback, they read during the previous year. How many subjects are needed? So there's your key word. How many subjects are needed? So you know you need a sample size to estimate the number of books Americans read the previous year. So you're looking at an average. Unless it says a percentage or proportion, you're always going to use the formula for means. Within one book, with 95% confidence. So initial survey results indicate that the population standard deviation is 16.6. Oh, another thing is, if you don't have sigma, you can use S. And that's probably the only formula where those two can be used interchangeably. Okay? That's usually a pretty what do I want to say? It's pretty rigid which formulas you use when you have sigma, which you use when you have S. Okay. So, sample size needed. Okay. Within one book, what's that? What part of the formula is that?
Standard deviation.
Say again? Mike?
Thought of standard deviation.
Within one book.
Margin of error.
It's the margin of error. Yeah. So they want the estimate, they want half of the size of the confidence interval to only be 1 unit. 1 unit. So the E part is 1. With 95% confidence. So we just found that z-score. What was that positive z-score? 1.96? With 95% confidence in a z formula, you never have to look it up again. It's 1.96. And then sigma is 16.6 books. So there you go. Remember the squaring. That can be hard to remember. Squared.
Sorry, what page is that?
This is page 420. And it's number 45. So what do we get, gang? Scott?
I'm kind of confused on, are we trying to find the margin of error?
We're trying to find, our goal is a margin of error of 1 unit. So when we find when we take this size of a sample, okay, and we calculate our confidence interval, this distance is only going to be 1 unit. The entire width of the confidence interval should be only 2 units. So that's like, we're meeting that goal. And we're going to be able to say that with 95% confidence. That's where the 1.96 comes from. Lauren?
Is E always gonna be 1?
No. It depends on the goal.
It'll give it.
Yeah. It'll say within so much percentage points, or if we're estimating a percentage or a proportion, or so many units if it's for a mean. What do we get, gang? Right?
1,059 rounded up.
So you got 1,058 and some change?
Yeah.
Okay, good. And you always go up. Always go up to the nearest whole number, never down. Because if you round down, you risk not meeting your goal. Okay, you always go up to the next number. So we would take 1,059 people sampled. Make sense? Do another one really quick. A poll conducted on November 16th through 19th, 2007 by American Research Group. So this is the next problem, same page. Asked American adults how much they plan to spend on Christmas. On gifts for Christmas specifically. How many subjects are needed? Okay, so there's your question. How many subjects are needed? You're looking for a sample size. To estimate the amount planned Christmas spending within $5 with 95% confidence. So again, the outcome, they want to be 95% confident, and they want their margin of error to only be $5. Okay? You with me? So 95% confidence, what's the z-score? 1.96. Got it. What's our sigma? Is that in there?
$82.25.
$82.25. And margin of error? Yeah, notice it says within $5. So it wants the entire confidence interval to be 10 units long. Double the margin of error. What do we get? 33?
Oh, yeah, I forgot to square it.
Easy thing to do, Emma.
1040.
Sorry?
1040.
1040? Is that after rounding up?
Yeah.
Yes.
Okay. So you get 1039 and some change? And you would go up to 1040. Okay. So you see how sample size formulas work? They're actually, you have to actually have some background before you can actually get started with your study. You've got to set up accordingly. It's expensive to take a sample, right? It's time, it's effort, and that equals money. Okay, so section 9.2. Now we're ready for 9.2. Okay, so in 9.2, think about our process here. Think about our process that we were just using, the confidence interval formula. And the assumptions behind those. So the assumptions were that so one of the assumptions in 9.1 was, okay, we're trying to estimate a mean, a population mean, because we don't know it. Okay? But how likely is it that if we don't know the mean, that we're going to know the population standard deviation? Doesn't that seem odd? Like, why? If we don't, the mean is like the most basic parameter around. So we don't know it, but we do know the standard deviation. So this almost never happens in reality. Okay? As you notice from the homework problems, that it usually comes about from a previous study or something like that. So in 9.2, we have the more realistic case, and that's estimating mu when sigma is unknown. Now to do this, and you guys have your notes, now to do this, it's a little tricky because if you're estimating using another estimate with the formula from 9.1, so if you're making an estimate based on another estimate, the normal distribution kind of falls apart. It can't handle the extra error involved when you have an estimate in that formula. So a new distribution was discovered to take care of that extra error, and that's called the student's t distribution. So the student's t was developed by a guy named Gossett. He was a lifelong employee of the Guinness Brewery. So he was all about developing agricultural methods to brew better beer. So they sent him to Cambridge and had him study statistics, and that was his whole life's work. But in the process, he made a lot of really cool discoveries. But Guinness wouldn't allow him to publish. So he published under the pseudonym Student. So that's why it's called the student's t distribution. So the t distribution takes care of the extra error involved by not having the population standard deviation known when you want to estimate a mean. Okay?
You say that again?
The t distribution takes care of that extra error involved when you're using an estimate to estimate a mean.
You're referring to the margin of error, you're saying?
Not really. Let me proceed and then see if I answer your question, Michael. So like where say the normal distribution might look like that, the t distribution might look like that. It's bell-shaped, it's centered around 0, but it's not a normal distribution. It's a t distribution. It's a little chunkier in its tails because it's absorbing that extra error involved. Mike?
Is it still symmetric?
It is symmetric, yes. Yes. So, bell-shaped, symmetric, mean at 0. Okay?
But not normal.
But not normal. It's abnormal. Okay? So the student's t distribution is the statistic is given by t equals, and this will look really familiar, x bar minus mu divided by s over root n. So when the sample standard deviation is in there instead of sigma, this thing turns to a t. And this thing has what we call n minus 1 degrees of freedom. So it's very, very, very based on sample size. It's very dependent on sample size. And let's see. We're not going to find probabilities like we did with the normal distribution with t. We're only going to be looking for these cutoff values in the tails. Okay? And that's where the new table comes in. And for the online students, this is in your appendix in your book. and I'll also scan one for you and put it on my website. Okay, so the t distribution, so you guys all have a t table, yeah? So it works such that you look up the amount of probability in the tail, okay? And then you go down the left-hand column to your degrees of freedom and you find that corresponding value. It's really, really easy. Not nearly as complicated as Z. So let's try. I'm just going to make up some problems. Is that all right? Because I don't really like the ones in the book for this. So let's find t of 0.05 when the sample size is 10. So on the Z table, the entire table front and back is only one distribution. I'll be right with you, Lauren. The entire thing. On the T table, every individual line is one distribution. So here, you're getting T distributions for all these different sample sizes. Lauren? Oh, can you share with someone next to you, because I'm going to need this one. This is my last one. I need it for and then I'll. Do you have a spare, Alex?
Yeah, that was the next one.
Oh, great. Awesome. Thank you. Okay, so to find T of 0.05 with a sample size of 10, you need to find your degrees of freedom. So sample size of 10, my degrees of freedom are 9. Okay?
Wait, so degrees of freedom, sample size minus 1.
Sample size minus 1. Yeah, sample size minus 1. So go across the top column till you get to 0.05. It's the 1, 2, 3, 4, 5th column. And then go down till you get to degrees of freedom of 9, and what do you get? 1.833. That's it. You're always going to get the T in the right tail. If you want the left tail, which we'll get to in hypothesis testing, you just stick a negative on it because of the symmetry. Okay? Does that make sense? If you had this T distribution, you're always finding the T in the right-hand tail on the table. You'll always find the one over here. Okay? In chapter 10, we're going to need the other side of the distribution from time to time. And if you've got a probability of 0.05 in the tail, then your T value over here is just going to be negative. Okay? Okay, how about, let's find T of 0.025 with a sample size of 50. What's your degrees of freedom? 49. And it's customary to write that as DF. Sometimes we just even call degrees of freedom DF. Now, do you have 49 on your table? No. So you just use the closest, 50, and that's okay. It wouldn't be that much different. You go to 0.025 across the top, which is the 1, 2, 3, 4, 5th, 6th column, and then down to 50 degrees of freedom, and that value is 2.009. Is that right? Okay. So the lines that you don't have in the table, don't worry about it. If you want, like, say 55, you could average the two T's of 50 and 60, and that would be okay. It's really, they're not that far apart. And that's why they skip a lot of the degrees of freedom toward the bottom of the table, because as the sample size gets big, then of course the sample is that much more representative of the population. And once it gets really big, and you can see at the bottom of the table a Z, it's practically indistinguishable from a Z curve. So as your sample size gets gigantic, you can just use Z-scores and you're fine. Does that make sense? Kind of, sort of? Okay, good, good, good. So let's use this puppy. Now, we can do the commute to work problem. Yay! Oh. No, I should tell you this first. Confidence interval when sigma is unknown. So it's a t-value. No, sorry. It's x bar minus a t-value times s over root n. So the only thing we're doing here, when sigma, the population standard deviation is unknown, and we replace it with the sample standard deviation, we have to switch from z-scores to t-scores. And otherwise the thing is just the same. You guys okay with that? Okay. And again, the assumptions or the criteria for this procedure is that, again, sigma unknown. And of course you can get S from your sample data, yeah? And then the other is that X bar is normally distributed. And the T procedure is really, really super reliant on X bar being normally distributed. So that's really important for any T procedure, okay? Okay, so let's get to our commute problem. It says a Gallup poll of 547 adult Americans employed full or part-time conducted August 13th through 16th, 2007 asked, how much total time in minutes do you spend commuting to and from work in a typical day? Survey results indicate that X bar is 45.6. And the sample standard deviation is 31.4 minutes. How many people did they, 547 people were surveyed. Okay.
What page is this? Sorry.
This is page 432. I'll write that. And it's number 17. Construct and interpret a 90% confidence interval for the mean commute time. So, your process, okay? I want a 90% confidence interval for the mean. A mean. So you have two choices. Z interval or T interval. You look back and you go, I have sample standard deviation, so you go T interval. Okay? So we've got X bar minus a T value times S over root N to X bar plus a T value sigma over root N. So we have X bar, we have the sample standard deviation, we have the sample size. We just need the T value, which is based on 90% confidence, and the sample size. So if we have a sample size of 547, what's our DF?
546.
546. Not that it matters, because I think we're going to have to do an estimate on the table. It's pretty far down there. So what would our T value be? You would find T the same way. You take your 90% take that 10%, chop it in half, and you have 0.05 in each tail. So you're looking for 0.05 in a tail with 546 DF. So we'll just use the closest thing, yeah? 0.05 down to, and course compass will give you the wiggle room, you know, for these degrees of freedom. Oh, geez. We've got 1.6, I've got for 100 degrees of freedom, I've got 1.660, and for 1,000, I've got 1.646. Is that what you guys see? Okay, why don't we average those? Because 546, it's kind of in the middle, don't you think, Scott?
I think you wrote the formula wrong on the upper bound.
Oh, I did, thank you. Thank you. Okay, so let's do the 1.660 plus 1.646 divided by 2. And we'll use that for our t-score. What do we get? 1.653. 1.653? Yeah, Lauren?
I have a question. Why are we looking at 100?
Because our degrees of freedom is 546, and so we got to look for the closest thing down the degrees of freedom column. So there's nothing even close to 546, right? So we'll take the one from 100 and the one from 1,000 and average them. Make sense? Good. Okay. All right, so we're set. Let's plug it in. So we've got X bar, 45.6, minus the t-score, 1.653. And I think you guys, if you use the 1.660 or the 1.646, I don't think you're going to have a problem. Times 31.4 divided by root 547. Okay, and when you go to put that in your calculator, it's pretty easy peasy. You just type it in as it occurs with this add, subtract, multiply. You can go 45.6 minus 1.653 times 31.4 divided by root 547. 43.38? Anybody else get that? Sound good? What do we get for an upper bound?
47.82.
47.82? Does that sound good to everybody? So again, our sample, the probability or the chances that our sample mean is going to be exactly the same as the population mean is slim and none. We discovered that, right? So what we do is build an interval of values that says how confident we are that the mean is between, the true population mean, mu, is between these two values. Okay? So now let's write an interpretation or talk about what that means. We are 90% confident that the mean, mean commute time for all commuters is between 43.38 and 47.82 minutes. Adult Americans, for all, we can say, this is for all American commuters. Or for all Americans, right? Because it's taken nationwide, do you agree? Okay. Does this make sense? Yes, Scott?
So from the step where you find out your tail pieces, which is 0.05, are you converting those into T?
Yeah, yeah. You're using the T-table. The probability on the Z-table, it was probability and Z-scores were corresponded. Here, it's probability, T-scores, and sample size, or degrees of freedom, all correspond to that one probability. Okay. Is it possible that the mean commute time is less than 40 minutes? Is it possible that that's true? Is it humanly possible?
Yes.
Yeah, sure. Because this is based on sample data. Is it likely?
No.
So the sample, the confidence interval is saying, if we took 90 samples of size 547 and constructed 90 confidence intervals based on those 90 different samples, okay? No, I'm sorry, 100 confidence intervals from those 100 samples, 90 of them would contain the true value of the mean. 10% wouldn't. So is it possible that the commute time is 40 minutes? Sure, because this is just based on our sample, right? Is it likely? Well, we're 90% sure that the mean is between 43.38 and 47.82. So is it likely? No. No, not really. But it can happen. Does that make sense? So again, if we constructed 100 confidence intervals of size 540, sample size 547, so they would all have their own sample means, right? And they would vary. A lot of them would overlap, some wouldn't. Okay? But 90 of those out of 100 would contain the true value of the population mean. Okay. So I want to go on, and we'll come back and do another problem from here later, but I want to just skim over 9.3 while we're here. Okay? In 9.3, we talk about confidence intervals for a proportion. Oh, we have to do this one on our calculator first. Yay! I was waiting for one of you guys to say, well, isn't that formula on our calculator? Yes, it is. And this is called T-interval.
Do you have a printout of this on your website?
It's on my website, yeah. So you go stat, right, over to the test menu, and then scroll down. In my calculator, it's number 8, T-interval. There we go. Number 8. Okay, so what I don't have on my website is I'm not going to tell you how to type in all this stuff in the menu. I mean, come on, right? You're supposed to know your notation, your definitions. So when you have stats, you have your stuff to enter, okay? As opposed to data. There's your sample mean, so 45.6. Then it's asking you for your sample standard deviation, 31.4. And your sample size, 547. So the calculator will calculate the degrees of freedom and the t-value for you. Then go down to calculate. T-interval takes another split second. 43.39 to 47.81. So we're off by 1/100th. That's okay. You should be fine in my stat lab. Because it'll give you the wiggle room needed for using the different technologies. Yay? Big time yay, huh? So section 9.3. So again, during the final, you're going to have confidence intervals. We're going to have 7 different ones. Hypothesis tests, which will start Monday. And sample size formulas. That's the only 3 things on your test. But you got to be able to choose the right test, choose the right method of inference, and you got to tell me what it means. That's your job on the final. Okay? How about you can go back and look at the video. Confidence interval formulas, confidence intervals, hypothesis tests, and sample size formulas. You got to choose the right method, and you got to tell me what it means. Okay, I'm on page 442. And I guess I have to tell you about this before we do a problem, don't I? I think it's all discombobulated today. Okay. So in 9.3, the deal is we want to estimate a proportion, percentage, probability. They all follow the same kind of method and criteria. So 9.3. Okay? And this follows 8.2, where we talked about the distribution of p hat. Okay? So we're estimating P. Population, proportion, percentage, or probability. And then if you recall, the distribution, so we have to know about the distribution of its sample statistic, which is p hat, in order to estimate P. And we found out that the distribution of p hat is normal if a couple assumptions were true. And those are our assumptions for this procedure. Or a couple criteria were true. So the assumptions are that n times p times 1 minus p has to be at least 10, and that the sample size is less than 5% of the population size. So those are your assumptions. And again, you're not going to have to worry a lot about the assumptions, because we're not going to give you, the book and on your file, I'm not going to give you anything that you haven't learned how to do. Okay, that would just be mean. Okay, so I want you to learn this stuff first. So the distribution of p hat is normal if those things occur. The mean of the p hat distribution is p. The standard deviation of the p hat distribution is root p times 1 minus p divided by n. And we can also standardize p. So the standardized version of p is a z-score. It's the cutoff value minus the mean divided by the standard deviation. And that's pretty much true for standardizing any variable. You take the cutoff value, or the value of the sample value, subtract the mean, divide by the standard deviation. A 1 minus alpha times 100% confidence interval for p is given by p hat. So you take the sample value, you subtract a z-score times the standard deviation, but now we're going to use p hat because we're trying to estimate p, to p hat plus some z-score times the standard deviation. So the standard error on p hat, for p hat, if we're trying to estimate p, we use p hat to find the standard error. If we're standardizing p, we use the mean has to be given. So we use that value to find the standard error. It's more accurate. Okay, so let's do a problem. Okay, and then we'll come back next time and look at it again. So I'm on page 442. Formulas are going to start getting a little uglier. 442, this is number 21. Okay. It says a Zogby interactive survey conducted February 20th through 21st, 2008 found that 1,322 of 1,979 randomly selected adult Americans believe that traditional journalism is out of touch with what Americans want from their news. Obtain a point estimate. Do you remember what a point estimate is? Good, Ann, yeah. The point estimate is the value of the sample statistic. So here it's the value of p hat, which would be x over n. So it's like the number of successes in our n trials. Okay? It says about 1,322 out of 1,979. There's your point estimate. And then, I don't know, we might want to, what is it approximately? 0.668. 0.668? So there's your approximate point estimate. B says, verify that the requirements for constructing a confidence interval for P are satisfied. Okay, I'm going to kind of skip over this. We're going to assume that n times P times 1 minus P is at least 10, and the sample size is less than 5% of the population size. And we want a 96% confidence interval for the proportion of adult Americans who believe that traditional journalism is out of touch with what Americans want from their news. Okay. B, I'm going to put check. So, yeah, 96% confidence interval for the proportion. Okay? For the proportion. You with me? Okay? So, these confidence intervals are so easy because all you need is x and n, there's your p hat, and your z-score, and that's it. Yeah. Yeah. And in fact, we're going to cut straight to, it's about this time in the course where I go, I don't want to sit around and simplify that. It's ridiculous. That's not the best use of our time. Okay? Let's just cut to the chase. But how about if we practice finding the z-score? Because you might have to do that with a confidence interval formula. Okay? So if we're just wanting to find the z-score corresponding to 96% confidence, (96% in the middle, 1 minus would be 4%, chop that in half, 2% in each tail. And then your negative z-score is here, and your positive z is here. So you're going to look up area of 0.02 on your z table, not your t table. Area of 0.02, what do we get?
Negative 2.05.
Negative 2.0.
I think that's the closest.
Yeah, it's right. The closest is 0.0202. That means on the positive side, positive 2.05. Okay? So let's use our calculators. I'm going to write out the interpretation. Okay, so hopefully you have time to stick around for that because we may go just a minute or two over. All right, so once you pull the x and the n out of your problem, and your level of confidence is all you need for a proportions interval. So you're going to go stat, right, and then go down, down, down in your menu. Go. You're going to want one proportion z interval. So that's this formula. Okay. X, N, confidence level, and you're good to go. So we've got 1322 out of 1979. Confidence level 96. And now you're estimating a proportion. So the numbers, the upper and lower bounds are always going to be between 0 and 1. Okay? So we've got 0.646 to 0.690. Saved to 3 decimal places, and my stat lab will tell you how many decimal places it wants. So 0.646 to 0.690. Okay. So to interpret, we are 96% confident that, okay, what were we estimating here? The proportion of Americans who believe traditional journalism is out of touch with what people really want. Let's say the proportion of all Americans, okay, because we are estimating a population value. With what Americans want, blah, blah, blah,
that's the confidence.
is between. So you have to let me know that you understand what this is telling you, what the confidence interval is telling you. Is between 64.6% and 69%. Okay? So again, you've got to pick the correct method of inference, and you have to tell me what it means. And that means talk about the problem. Whatever the problem is, I want that in your write-up. Okay? And we'll talk more about that in the next few weeks. 4 classes left. Thank you. Have a good night. Thank you.